So, in fact, अगर yeah, so ये जो representation, that is the these are the matrix elements not only for the diagonal but also for the off diagonal. लेकिन अगर original basis में देखें तो these matrix are elements are only for the diagonal, but we have sort of generalized this. So इस चीज को point out कर लें. So in because अभी जो definition लिखेंगे इस K की जो आप in fact जिसके matrix elements हमने ये लिखे हैं, इसकी डेफिनेशन से आपको ऐसा लगेगा दैट इज it is talking about the off diagonal elements only, but in general it is basically for the diagonal as well as for the off. So basis की definition की मदद से वो diagonal की के elements की matrix elements लाएंगे, but in general it is true for both. Yeah. So uh, in the original basis, that is in the basis जो हमने बात की थी के आई. Yeah. Then the operator K जो अभी आपने डिफाइन किया है was supposed to be diagonal. Diagonal expressed as कैसे लिखा था K which is equals to sum over I Ki and Ki Ki. So this this cat bra notation जो है वो बुनियादी तौर पर प्रोजेक्शन ऑपरेटर को रिप्रेजेंट करता है. And you should remember that this is basically an operator. So this is some operator projecting a particle in the ith state. So this would be some complete basis of states. And in those complete bases of states, and in those complete bases of a state, a particle is being placed. Yeah. And so that's why it is only for diagonal, but it is also true for the off diagonal case. So in fact, uh, uh, and this is uh, so in any case, uh, such simple additive, simple additive, one particle property is uh, is seen to be quadratic. Quadratic in the creation annihilation operations. In creation, public annihilation operators. Okay. And so then if there are two particles, then there has to be an interaction term involving two particles. And then because there is an interaction term involving two particles, then there has to be an interaction potential energy जो कि हमें define करनी है. So interaction term involve two particles. Right? And interaction energy then is required. Interaction energy. इस केस में potential energy. Can be defined as. So remember when we talk about so we talk about our sun, which is made up of protons. Yeah. And so how is it possible that there is those so many protons and they are living in the same state? So two fermions cannot be in the same state. They can only be in the same state when if and only if there is at least one quantum number which is different for those two protons, yeah, or two electrons, yeah, and that is basically the spin, yeah. So if one is in the up spin, the other one is in the down spin, yeah, and so this would create some sort of an attraction, some sort of an attractive property which basically forces those two particles to stay in one state, stay in a state, yeah. But then there are also the gravitational forces, and then there are exchange forces and Coulombic forces that would lead to some forces which try to repel those particles and some forces which try to sort of combine those particles. And there is a balance between those two forces, and that's how the structure of this celestial object, sun or any star, is maintained. But then if the number of particles or protons decreases, then this balance is disturbed, and then we have some sort of a neutron star or a black hole. Yeah. So these interaction terms are very important in the description of those celestial object as well. So let's say we have this potential energy, and let's say मैं इसको एक artistic V से जाहिर करता हूँ in order to differentiate from the other. So half summation over I is not equals to J, and we would have Ni, number of particles, Nj, number of particles, and then there is an interaction term Ij, Vij. Plus, there are other states as well. So, the second term, एक और term हो सकती है when there are more than one particle in one state. So that is true only for bosons, but not true for fermions. Yeah. So there could be a second term, and this second term would be to correspond Ni into Ni minus 1. So this is basically some sort of arrangement or permutation. Yeah. But the second term is only there when you talk of more than one particle in one state. So uh, the second term occurs when more than one particle in a state. In, in a state. But then this is just for a boson. Now, again, we are talking about fermions, then using the definition of a number operator, Ni, which is equals to किसके बराबर AI dagger, and AI, then हमारी जो equation है, this would the interaction potential energy would become the first term only, summation over I j AI dagger A j dagger A j A I. I and Vij for let's say for bosons or fermions. Yani even if we do not talk about second term, then this first term is valid for both bosons and fermions as well. So this is true for bosons as well as for fermions. The first term is always true. Yeah. The second term is there whenever we talk about bosons. But in case of fermions, the second term is not true. So this is in the diagonal representation. We need to transform into some other representation. So this is in diagonal representation. Yeah, transform to some form to an arbitrary uh, representation. Uh, yeah, so that could be, for example, AI dagger changing to summation over Q, BQ dagger, LQ, KI. Yeah, and so on. We could have more than such representation. और अगर ऐसा है तो then this equation for जो हमने लिखी है equation for basically V वो हम चेंज कर सकते हैं that equation जो हमने वो ऊपर लिखी है this equation, yeah, so this equation, sorry, it is equals to half time this. So for this equation, then we could write it as, which is equals to half summation over ij summation over q r s and t, because then we change it for different states, because यहाँ पर दो हैं operators, yeah, and I or J, and those I or J would correspond to Q, R, and ST. दो चार हो जाएंगे. So we have B Q dagger, B R dagger, B S and B T. That is two for creation and two for annihilation. That's why we have I and J would correspond to both for the creation operator as well as annihilation operator. So for the creation operator, we are using the subscript Q and R. And for the annihilation operator, we are using the subscript S and T. And correspondingly, those overlaps. And that those or the inner products. So the inner products LQ with KI, the inner product of LR with KJ, the inner product KJ with LS, then this is for the, in fact, the annihilation operator, and the inner product KI with LT, and then the interaction potential Vij. Yeah? And so अब अगर हम देखें तो we can again use this this quantity. अगर आप इस quantity को लिखना शुरू करें I और J को, so again you can define the matrix elements of some operator. Let's say we define an operator. Uh, so consider defining an operator V. Operator V through the use of the two-body eigenstate. And two-body eigenstate क्या है? Ki, Kj. This is the two-body eigenstate. And this operator जो हम define कर सकते हैं वो क्या हो सकता है? V operator summation over I and J. We have Ki, Kj, and then there is Vij, and then we have Kj or Ki. Yeah. So this is a new proton. Then ये कैसे अब आपने हासिल किया? By rearranging this this term. Yeah. And so we would have this rearrangement would be equals to half summation over QRST. Then your operators BQ dagger, BR dagger, BS BT और अरेंज कर लें आप LQ LR, yeah, and then the matrix. So this is summation over IJ and KI, KJ, VIJ, KJ, KI. We have a bracket closed here, and then LT or LH. Yeah. So this is the rearrangement और इस पूरी चीज को, ये जो पूरी चीज है कहाँ से कहाँ तक, यहाँ से यहाँ तक. This is basically V, which could be written as LQ, LS, sorry, LR, yeah, and then we have a bracket summation over IJ, KI, KJ, VIJ, KJ, KI, this, or then we have LT, LX, yeah, and so our interaction potential becomes half summation over QRST, BQ dagger, BR dagger, BS, BT, and that is in fact QR state. We have Q and R state, and the matrix element is of operator V, and we have P and S state. So the matrix elements of P. So this is the general form of any two-body interaction. In some vague sense, Q is the is coupled to T via the intermediate state Ki, while R is coupled to S via intermediate state Kj. And this is basically the concept of multiparticle states. Yeah. So this is the general form of any two-body interaction. So in some vague sense, Q is coupled to T. किस रास्ते से? via an intermediate state state Ki, while R is coupled to S via an intermediate state Kj. So this is important. This is important consideration जो आप बुनियादी तौर पर क्वांटम फील्ड थ्योरी के अंदर डिस्कस करते हैं. Why there is a need for a multi-particle quantum theory? Why not the single particle quantum theory जो कि हम non relativistic quantum theory करते हैं in lower classes is sufficient. So there is basically some there has to be invented a new theory which is a multi-particle theory, quantum field theory, which relies on the fact that the need for the new theory or multi-particle theory is basically this जो हम यहाँ पर ये साबित करें. बट अगर देखा जाए तो इंटरेक्शन बुनियादी तौर पर किसके दरमियान हो रहा है? इंटरेक्शन हो रहा है दिस ऑपरेटर्स की मदद से, जो ये एनाइलेशन और क्रिएशन ऑपरेटर, and which involves the destruction of particle in state S and T, followed by creation of new particles in state Q and R. Yeah. So there is a destruction of particle in S and T state, and this is followed by a creation of new particles in state Q and R. And because particles are indistinguishable, we can't say anything about their identities. And so by symmetry, Vij जो है, जो interaction potential हमने ऊपर लिखा है, is same as Vji. And that's how, in fact, the matrix elements are also interpreted as well. Yeah. So this is something which is important. So, but in truth, the interaction, and what is the interaction? The interaction is, in fact, this term, BQ dagger, BR dagger, BS, BT. And what does this implies? It involves the destruction of particles in state state S and T, followed by uh, creation of new particles in state Q and R. In state Q and R. Now, क्योंकि particles indistinguishable हैं, so the interaction potential है Vij, that would be same for or is equals to Vji. So because particles are indistinguishable, one can't say anything about their identities. And by symmetry, Vij is equals to Vji leads to QRVTS equals to RQVST. आ, ये जो मैट्रिक्स एलिमेंट्स हैं वी के वी ऑपरेटर के, इनको एक डायग्राम से भी जाहिर किया जाता है, जिसको फेमसली फाइनमैन डायग्राम्स कहते हैं। और इस बिकॉज फाइनल डायग्राम अभी हम इसमें नहीं कर रहे हैं, लेकिन बाहर इनको लिखा जा सकता है। समटाइम दिस मैट्रिक्स एलिमेंट्स, ये मैट्रिक्स एलिमेंट कौन से, ये वाले और या ये वाले, दोनों एक ही हैं। मैट्रिक्स एलिमेंट इज रिप्रेजेंटेड बाय अ डायग्राम, बाय अ डायग्राम। और वो क्या है, तो इसकी बुनियादी तौर पर कुछ इस पर। दिस इज क्यू, दिस इज R, this is T, this is S, and this is basically the interaction involving. So this is the final state, and this is the initial state. Initial state of two particle system and final state of two particle system. अच्छा, then finally इसकी मदद से you can develop some sort of a Hamiltonian, जिसमें ये टर्म्स आ रही होंगी। और देन उस तरह के हैमिल्टोनियन को इस्तेमाल करते हुए वी कैन बेसिकली डेवलप अ फॉर्मलिज्म फॉर मैनी पार्टिकल डायनेमिक्स, जिनके टाइम डेवलपमेंट के लिए हम कोई सिमेट्राइज्ड, करेक्टली सिमेट्राइज्ड स्टेट्स डिफाइन कर सकते हैं। सो दिस हैज सम वेरी यूजफुल यूटिलिटी। So this can be used uh, for 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 constructing in a Hamiltonian uh, containing some term, then we can employ some formalism for many particle dynamics, or many particle dynamics to get the time dependent development of correctly symmetrized states. Right. So this is basically something which is important. Now let's say one final topic जो हम करना one or two final topic जो हम करना चाहते हैं because we have proved our point that quantum mechanics is not a single particle theory, but quantum mechanics is a multi-particle theory. And then if we could develop some sort of a Hamiltonian, then we could talk about the eigenstate, eigen values, and so on. And then using that Hamiltonian, we can write the dependent development of those correctly symmetrized states. And so the important point which comes here is, in fact, the multi-particle nature of quantum systems. Yeah. And so this is the starting point of quantum field theory, where we talk about, or the relativistic quantum mechanics, where we talk about that uh, it is not just a single particle theory which is important. It is basically multi-particle theory. So let's introduce the field theory. And let's introduce the continuous spectrum, by the way. What we need to do here, yeah, is basically the continuous spectrum. But in the passing, we would basically be introducing the field theory. Yeah. So let's start continuous spectrum. Spectrum. And in fact, this topic would lead to introduction to field theory. Okay. So let's say we have some one particle states which are eigenstates of position variable r, and for a certain value of sz, that this sz could be some property, some intrinsic property. And this sz property, sz implies here for the z-axis, and s implies for maybe symmetry and antisymmetry. And this symmetric or antisymmetric states are basically those which corresponds to bosons and fermions. So that would correspond to half integer or integer spins, and that would correspond also to some variable, let's say sigma, which is plus or minus one. That is in terms of symmetry. Yeah. So let's say we suppose uh, our one particle states. Suppose our one particle states are eigenstates of position r for a certain value of z, certain value of s subscript z, denoted by sigma, which is plus or minus 1. Yeah. And these states are normalized. कैसे? These states are normalized as r prime, sigma prime, r double prime, sigma double prime, is equals to delta function in 3 dimensions of r prime minus r double prime and delta function, Kronecker delta function, sigma prime and sigma डबल प्राइम. या सो द नॉर्मलाइजेशन कंडीशन इस तरह से दी हुई है दोनों के लिए, दोनों वेरिएबल्स के लिए, आर के लिए भी और सिग्मा के लिए भी. ठीक है. सो आर के लिए इट इज 3 डायमेंशनल ड्रैग डेल्टा फंक्शन एंड सिग्मा के लिए क्रोनेकर डेल्टा फंक्शन. Then we can postulate creation and annihilation operator defined at continuous values of R. So we would say that the creation and annihilation operator is acting in such a way that it is basically for the continuous values of R, and and this would create, in fact, or destroy, obviously, for the annihilation operator. It would create and destroy particles of correct symmetry. That is, the use of this sigma is ensuring that the symmetry is correct. That is either for bosons or for fermions. So uh, then one postulate creation and annihilation operators operators defined at continuous values of R, which create or destroy particles of correct symmetry. Yeah. And what are these states denoted by? So these are denoted by psi, psi, sigma prime, r prime, and psi, sigma prime, r prime. Instead of in, instead of AI dagger and AI. So rather than using AI dagger and AI, we use psi dagger subscript sigma prime r prime and psi sigma prime of r prime. Yeah. And so we are basically now representing those, because AI dagger and AI represent state space, because these are the operators which creates or annihilate particles. And a particle is analogous to a state, by the way. Yeah. So we represent, instead of using AI dagger and AI, we use the symbol psi and psi subscript sigma prime r prime and psi sigma prime r prime without dagger. Yes. And now we postulate as before वही relations जो इस